Hello, everyone. So, thank you for the introduction. Indeed, I'm a fourth-year PhD student. I've been working on typing Elixir for all this time, under the supervision of Giuseppe Castagna and José, who wanted someone to handle that for him. So I want to, in this talk, give a bit of showing you how it works under the hood, what kind of problems we're solving in order to bring types to Elixir. And I'll start with giving a bit of review of what we've done so far. So last week we introduced types into Elixir on the release 1.17, and this was about giving a foundation for types. So introducing base types, binary, integer, float, introducing an atom type with precise singletons. You can represent the type OK or error, or you can represent booleans, true or false. We had map types, being able to represent a map of any value, an open map, with the key type set to an atom, or just a closed map with just two fields defined x and y. For more complex types, tuple list functions, we just had base types, meaning any function just has type function. And anything else we couldn't type at type dynamic, and because those are set-theoretic types, we always support high-level operations and or not, which have the intuitive meaning that if something is of type T1 and T2, it has both types. If it's of type T1 or T2, it has either of the types, and if something has type not T1, it has any type but this type. And because we see types as representing sets of values, the type integer represents all integers, the intuition is that this corresponds to sets. So if we were using sets instead of types, we would have operations, union of sets, intersections of sets, or taking the difference of two sets. So I will use those signs sometimes. So thanks to this, to bringing those types, we're able to address some bugs. So when you're pattern matching on some maps, and because we know what kind of keys are in these maps potentially, we're able to tell you if you're trying to pattern match on a key that doesn't exist because you made an error in the name of this key. Similarly, because we know the type of user going around, we can ask questions. The type system allows us to ask question: does this key exist? So that makes us able to find if user address is going to succeed or not. Because we know that modules have to be atoms, we can also check if user is never an atom, then this function call on it will never succeed. And we have another class of error, which is that because we know now about integers, strings, binaries, when we do a comparison, we can see if we are going to compare, we can see if the types we're comparing are going to be the same at some point. And otherwise, it just doesn't make sense to do such comparison. Finally, rescued exceptions being structs, we could finally check if the fields that we're rescuing from them existed. So in those bugs, there are, I would say, two different sorts of bugs. Those that we solve by having a precise representation of types and being able to ask questions about them. So those would be the ones about maps and checking their keys, and those that come from checking if what we're doing makes sense, thanks to the type information that we have at hand. And in 1.18, we added composite tuple types, being able to represent a pair of integers booleans. List types, being able to precisely have, so this list integer PID is a list of integers that ends just by a PID instead of an empty list. It's an improper list type, but usually you would just use a list of atoms or integers or whatever you want in your list. And we started doing type inference of patterns. So functions being defined using patterns mean that we can ask the question, given a pattern, what is the type of values that match this? And in this case, it's the pair of any values. A term being a type that the type of all values that exist. And because we are doing this inference of patterns, we were able to start doing checking of function calls, because if we know the type of values that can come into a function with an approximation by approximating the patterns, then we can know when a function is always going to fail. So similarly, this gave us this allowed us to solve a certain class of bugs. The first class being we have tuples and we represent them precisely. So now we can check when we're doing something that's not going to succeed, such as accessing an index, the third element of a tuple. Same, we can we can check if list operations are going to fail or not, and then because we're doing the analysis on patterns, and because we have the types at hand to progress into that analysis, we can find a certain class of bugs, such as if we have a pattern here that never matches because x is equal to y, and x has to be foo and y has to be foo, so the type system is going to find that there is no type that matches this at all. And we extend that to every construct of Elixir. So the general method that we have to improve the type system now has been to add more ways, more precise ways to represent the types that we need. So for tuples, for maps, and for functions later, and to type precisely the expressions in Elixir. So if we have, so here we type this function, this map with the type of maps that have one key foo set to an integer, and to ask questions about these types. And those operations, if you have a representation for types that is sufficiently rich, such as the one that we have for maps, for instance, those are not trivial questions. What's the type of the foo map, the foo field in map, and what happens to my type when I put some key inside of it? And the next release is going to bring more of that. So what's ready is that we have now a representation for function types, for precise function types. We have map domains. I'll show what those are, and we have a more precise typing for map and get. So there are other things that will come for this release, but those are the ones I want to talk about right now. And the goal with improving constantly the kind of types that we can represent is to be able to completely handle the guards of Elixir. So we can find even more inconsistencies or errors in your test, in your code. So Elixir has guards that check if some variable is a function of a given arity, and you also have function calls that explicitly pass a certain number of arguments. So it's important to be able to represent that some expression as really a given type with a given function type with a given arity. That means that you can now type this sort of code where you go. So curry is a function that receives a function. It has to be of arity 2, and it transforms it into a function that receives an argument and returns a function that receives an argument that finally applies f. And with the proper representation for functions, you could write a type annotation for that. So this is indeed this corresponds to the first case of the first head of the function. We receive a function of arity2, and we return a function that returns a function that returns any value, because that's what we gave to the function in the first place. And because using type intersections, we are able to treat all the cases, all the heads of this function. We also do that for arity3. So so the language itself forces us to have sufficiently precise representation for types in this case. Maps with domains, they allow us to specify not only the type of one field, but the type of a whole class of fields. So if you want to if you want to use a map to store some sort of computation on floats, you're going to be able to say that the float keys in this map, they map to other floats. For instance, here, the cost map function receives a list of floats, and it returns a map with some tag that tells you what function I computed, and then you expect that when you manipulate this map afterwards, you will always get floats when querying floats on it. So the representation for maps is a bit complex, but we need to make sure that you can trust the operations that you do on it, or rather, you can trust what the type system presents you about them. So, for instance, let's say you have a base map which has two fields. A is a number, and B is the atoms OK or error, and you're going to and you want to subtract two other types from it, the types M1 and M2, which corresponds to just a basic pattern matching expression. So if you add this map of this type, and you pattern matched on maps with A float and B OK, you did something. Then in the second branch, you pattern match on this other type. In the third branch here, the type system, in order to determine the type of a map, is going to take its initial type and subtract the type of the previous branches. And then, if you use map A, if you call map A in this third branch, you want to have the actual type, the actual thing that you will receive. So this is a nice trick that we do in the system, is that in order to recover this type, we're going to take those three types, M0, M1, and 2, but in general, you could have many other fields. This could be a huge map, and you could have an arbitrary amount of subtracted maps. And a map, you can see it as equivalent to the same map if you split it in two, and you took the type it has for a given key, and the rest of the map without this key. So we use this equivalence, and then because we have a certain way to eliminate negations when they appear on pairs, we just do that. This is literally what the system will do underneath. So now that we have split those three types into pairs, where the first element is the type of the key we're searching, and the second is the type of the rest of the map without the key, we have a simple subtraction rule for pairs. Imagine you have a pair of types T1, TA, and RA, and you want the type of TA and RA minus the pairs of type TB and RB. And there are two cases for that. Either the first element of a pair is in TA but not in TB, and then the second element can be anything, so it's RA, or you have an element which is in both TB and TA and TB, and in this case you must make sure that you're not in the subtracted pair. And so you have this little rule, and we apply it. We apply it to this P0 minus P1, and we get two pairs. And now we apply the other subtraction of P2, and this gives us a list of pairs. And because we actually want to compute the type of a given key, we just take their first element. And so now you can see in 1 and 2, we obtain pairs integer RA or pair non and something. And if we gather all of these, we get the final type for A, which is integer. So that's the way we make sure that we're not the set operations that we do are not giving us imprecise types, and that you can trust them. So the point of having very precise types is that we want to analyze guards. We want to be able to when we have built-in functions in guards, we want to be able to express the contract on a type that is given by those. And there's also an inherent complexity within guards, which is that they use and, or, and negations. So here's like quickly how we tackle that. So if we have simply conjunction, we just refine the types of the variables as we progress to the guard. So here, process data is going to, when we have is-tuple data, we know that tuple data is a tuple, and then when calling tuple size data, we see that the only possibility is that data has to be a pair of any types. We can, because we have composite types, we can go deeper into that, and we can add that we want actually the second element of X to be some integer. And now, with this deeper refinement, we'll have that X is actually a pair of term and an integer. So this is how we handle conjunctions, and disjunctions are a bit more complex, because it's not only about analyzing one guard and the other and saying that values that succeed this guard are one or the other, because actually the success of the first guard influences what goes on in the rest of the guard. So we have to consider that when doing the analysis. So here, if we have is-tuple and tuple size X is 2, if this is true, we know that the first that X is a pair, and there's no other constraint on Y. And if this is false, we know that X is not a pair, and that Y is a Boolean. But the guard could actually fail. So if we have a guard where we simply ask straight out of the box, is tuple size of X 2? If X is not a tuple, this whole guard will fail. So you cannot say that actually if it was a Boolean, it would have succeeded. And so we have this, we include this error case into the analysis. And now if X is a tuple, tuple size of X being 2 may succeed, in which case it's a pair. But if it doesn't, X is still going to be a tuple for the guard not to fail. And we evaluate the rest of the guard with this assumption. And in this assumption, is Boolean is never going to succeed. So the only values that make this guard succeed are pairs, simply pairs. We do a similar analysis for negation that I will... do I have time left? Okay, so we do a similar type of analysis for negations, where we check what happens if the first guard succeeds, and what are the conditions for the rest of the guard. And so there are 2 types of refinements: refinements that come from actually the guard success, and refinements that come from the execution of the guard. If the guard succeeds, what can we know about the type of the variables? And we've progressed a lot into being able to cover all the built-in functions that compose guards. Now that we have functions with given RT, we can handle the isFunction guards. We have the composite types that allow us to express things such as isInteger of xfoo. And what remains is to do this precise flow analysis to exactly perform inference on guards, and even refine even more the checking that we do on functions. So key takeaway is that we're adding very precise function types to the next release, map domains, and that we're progressing on the guard analysis. And I know it's lunchtime, but I hope you enjoyed you enjoyed this little meal of type theory. Thank you.